All right, this should be the last video, I think, about inverse functions. And in particular, we'll look at a cool relationship with inverses and composition of functions, which we've talked about previously. So let's just use an example to show some of these neat characteristics. Let's say we were asked to find the inverse. We'll get a chance to find one more inverse function together. And let's begin with a radical function. So let's say we've got f of x equals to 2 plus the square root of x minus 4. And we could graph this to observe what I'm about to share, but I'm just going to make a note here that the domain for the function f would be all real numbers from 4 to infinity, including 4. And the corresponding range, again, we could verify this together graphically, but if you plug in that lowest domain value, the corresponding output is 2, and then it goes to infinity. So I'll just graph it real quick to validate what I just said about domain and range and share that graph with you. Okay, I went ahead and used Desmos to graph the 2 plus square root of x minus 4. And we can see that this radical curve, like we expect for radicals, has more or less a starting point. And we can see that that value corresponds to 4 for the x value and 2 for the y value. So hopefully that kind of makes the domain and the range that we just talked about a little bit more understandable, just looking at it even graphically. So now let's go ahead and dive into finding the inverse function. So I'll write the function again so we can move through that 4-step process that we're getting more comfortable with. So again, our function f of x that we're working on for this problem is 2 plus the square root of x minus 4. So we'll begin by replacing f of x with y. Replace f of x with y. Always a good starting point for this finding an inverse process. So now we have y equals 2 plus the square root of x minus 4. This next step basically involves generating the inverse. So as soon as we swap the x's and y's, we're actually at the inverse function. So I'm switching colors just to remind myself that when we swap the x's and y's, we truly are at the inverse. But the orange equation I have written there doesn't currently look like regular function notation. So we're going to work on solving for y to make it feel more like a function we're used to. That'll take a couple steps, and then we'll be able to end with good inverse notation. So to solve for y, it looks like I could begin by subtracting 2 from both sides. And then we have a square root function. So actually within this inverse process, we're using an inverse. So to undo a square root, we need to square both sides. And what's great here is on the left, that just stays as the quantity x minus 2 squared. On the right-hand side of the equation, the square and the square root basically cancel each other out. So we just have y minus 4 remaining. And then getting y alone just involves moving 4 to the other side by adding it. And I typically like to just flip-flop to get y on the left side of the equation. Feel free to do that too if that helps it look a little bit more normal. So now we're ready for our fourth and final step, which is just replace y with f inverse of x to get that good inverse notation. So in this example, looks like f inverse of x will equal x minus 2 quantity squared plus 4. That's the inverse. So I'm going to go ahead and graph that inverse function, plot it on the same graph of the original function to keep building that visual recognition of a function and its inverse. So I'll be right back. Okay, I've got the graph ready. So we have a little bit to talk about here because when I graph the original function, shown in blue here, and I graph what we just found for the inverse function, something kind of interesting happens. And maybe you can see a little bit what I mean. Let's talk again about the domain for f. So the domain for f, we had mentioned a little bit ago, was 4 to infinity. So the inputs or the x values for the function. Similarly, we had commented on the range for f, and we had said that goes from 2 to infinity. Now, when I graphed the inverse function in Desmos, it created a parabola, right? And we probably expected that. It involved a squared term. But there is one important thing we know about the domain and the range of an inverse function, and that is they're basically the flip-flopped domain and range of the function. So the domain of f automatically becomes the range of f inverse, which means the range that we're working with should actually be 4 to infinity. Similarly, the range for f should become the domain for f inverse. So that tells me we should be looking at a domain from 2 to infinity. So Desmos didn't know that when I graphed the function, so it graphed a full parabola. But in order for f and f inverse to be inverses visually, can we tell that we really shouldn't be including this side of that parabola, right? It would only be half of the parabola to get that mirror image over this line y equals x. So I would want just this little piece and that little piece. So we have to restrict, it's called just restricting the domain to make sure that the inverse function is truly what we want. So just the right half of the parabola is what we would take to be the inverse function. There's a very similar question to this on exit slit 4, so I hope that you find this helpful as you work on exit slit 4 also. But the point of this video was more than just finding an inverse and probably even more than domain and range discussion, although I think this is valuable. Let's go back to the beginning. We had began with talking about there's this cool relationship with inverse functions and composition. So I'd like to wrap up by talking about that relationship. Now, between a couple pages on the screen here, we have a function f, and we found f inverse. So I'm going to go ahead and make a little bit more room just to recap what we found. We found, or rather we were given, that f of x was 2 plus the square root of x minus 4. We went through the process of finding an inverse function, and we found f inverse to be the quantity x minus 2 squared plus 4. So now what I think I'd like to do with us is look at this relationship from a composition. Let's try finding the composition of f and f inverse. So similar notationally to what we did a couple videos ago, we looked at f of g of x kind of notation. Same principle applying here. So in order to find f of f inverse of x, some of you have benefited from this intermediate step of replacing f inverse of x with its equivalent expression, which is going to be x minus 2 squared plus 4. So now really what we're doing, I'm writing these parentheses real big to remind us, is we're evaluating function f at the input of this x minus 2 quantity squared plus 4. So that means I run back up to function f, and anywhere I see an x, I'm going to input this whole quantity. So I'll go ahead and show some steps for that. So function f says take 2 plus the square root, and then in place of x, I'm going to insert the whole quantity x minus 2 squared plus 4. And then I won't forget to subtract 4 underneath the radical because, again, that's what the original function f had me doing. Now, as we simplify this, notice what happens. The 2 out front is good to go, right? And within the radical, I've got the quantity x minus 2 squared plus 4 minus 4, which is just the quantity x minus 2 squared. The plus 4 and the minus 4 cancel out. And when we have a quantity under the radical squared, it simplifies to just the quantity, right? So for example, if I had the square root of 3 squared, the squaring and the square root cancel out, so it would leave just the 3. In the same way, in this problem, the square root and the square cancel, leaving just the quantity x minus 2. But if I continue simplifying, that now means I've got 2 plus x minus 2, which simplifies to just x. Okay, that's cool. So far we found, I'll just summarize, that the function composed with the inverse is equal just to x. So I'm going to go ahead and box that off as our first result. I wonder what would happen though if we reverse the composition. So notice for most f of g and g of f kind of compositions, it's not true that they're equal. But let's try reversing the order of composition here. Okay, and I'll scroll back and forth a little bit to help. But we're just taking the order we did at the beginning and reversing it. And I'm going to use that same intermediate step that I used in the example above, which is anytime I see the f of x function, I can replace that with its original definition. You can verify this is true. That original definition was 2 plus the square root of x minus 4. And I'm evaluating the inverse function now at that input. Okay, so probably you have these functions written down and can pull them back. But again, f of x back at the beginning was 2 plus the square root of x minus 4. Now, that becomes the input for the inverse function. And the inverse function said take the quantity x minus 2 and square it and then add 4. But the x is now replaced fully by this input. So I can insert 2 plus the square root of x minus 4 as the input for f inverse. Now let's go ahead and simplify. So I see my plus 2 and my minus 2 cancel. So in the parentheses, I've really just got a square root of x minus 4. That quantity is being squared, and then we add 4. So when I square the square root, it pops off, leaving just the quantity inside, which is x minus 4. So the square and the square root cancel out. And then when I combine the like terms, the two 4's cancel out, so I'm left with just x. So I'm going to summarize again on the side like we did in the last one. So f inverse of f of x is equal just to x. Turns out that what we're finding right here is a special relationship with functions and their inverses. So just to draw your attention now, when we compose f and f inverse, we get x. When we compose f inverse and f, we also get x. So I'll end with kind of making a statement of fact here, which is that given f of x and f inverse are inverse functions, right? Notationally, we understand f inverse means the inverse function. So given that these two are inverses, it is always going to be true that f of f inverse of x is equal to x, and f inverse of f of x will also always equal x. So that is a true statement of fact for two inverse functions. And that's great because that means it kind of gives you another way to check your work. If you find a function f inverse and you want to make sure you did good work, try composing it with f and make sure you get back just x. Pretty neat stuff. So last little thing, we've really exhausted this example, but I'm just going to wrap up with one last connection to domain and range. Throughout this video, we worked with function f being 2 plus the square root of x minus 4, and we worked with finding that f inverse of x was the quantity x minus 2 squared plus 4. We knew that the domain for f was 4 to infinity, and the range was 2 to infinity. That informed us immediately about the domain and range of f inverse. The domain of f inverse was just the range from f, and the range for f inverse was just the domain for f. So if you ever were to encounter a question where you're told a bit of data about f in terms of an xy pair, you can immediately inform f inverse. What I mean by that is I could say that f of 4 is equal to 2. And I'll go back to the graph real quick to verify that with you all. F of 4 is equal to 2, right? That means that when x is 4, y is 2. Okay, and graphically that matches up. So that means if I were to then ask you about f inverse of 2, what would that tell you about the output? So remember, this is an x value for f, this is a y value for f. For the inverse function, the x's and y's flip. So now 2 is an x for f inverse. So what's the corresponding output? Well, it's going to be 4. It's got to be 4 because the xy pair got flip-flopped. So notationally, it can take just a little bit of getting used to, but hopefully that connection feels a little bit more clear. All right, we've reached the end of inverse functions. So next time, we will be talking more about transforming functions.